there is a conservation law associated with each of these properties, right? That's from physics. Okay. So based on those, then we had a general equation, right? So I'll just repeat that general equation that we obtained, which was essentially accounting. Basically, you're accounting for something. So general, we'll have del psi by del t plus del dot flux of the property psi was rate of generation of psi. And this I might have changed the notation here. Well, I earlier wrote something else, but this is rate of generation of property psi. This is basically accounting. Okay, nothing more than that. Net in is equal to net out plus generation, etc. Okay. Now, this we saw that this flux is the overall flux of the property psi. This will consist of, in general, it may consist of two parts. Okay, one would be convective, and one would be diffusive. Okay, convective, we have a very simple relation available. At any point, the convective flux of psi is given by psi times, where psi is the property capital psi volume, what I'm referring to as small psi. Okay. So psi times local velocity v, that would be your convective flux. Okay. That you can check. This is basically capital psi per unit time multiplied with velocity is length by time. Sorry, per unit length, per unit volume. So psi per unit volume, that is L cube, and this is length by time. This is essentially L squared. So psi per unit area per unit time. This is equivalent to psi per unit area per unit time, which is the psi flux. So flux of any quantity is basically psi crossing per unit area per unit time. That's the meaning of flux. Okay. So, so it has the dimensions of psi divided by area into time. Okay. Whatever the psi is, the corresponding dimension. And the diffusive flux, this relation, this we get from constitutive relationships. Okay. Because this involves, well, basically the convective flux has nothing to do with material property. It has all to do with the transport. Okay. This has nothing to do with material property. If you have two different materials, as long as velocity is the same, the flux will be the same. Okay. However, the diffusive flux, the constitutive relationships give us the form of diffusive flux. Okay. So basically, diffusive flux will depend on what material you are, where the flow medium will be actually playing a role in. Playing a role in finding out the diffusive flux. Okay. So form of and generally speaking, so basically, what kind of material property comes into picture? That's diffusivity kind of material property comes into picture. Every property will try to diffuse away if there is a gradient in that property. And generally speaking, that is given by there is some kind of concentration gradient multiplied with a constant of proper proportionality, which is dependent on the material behavior. Okay, so diffuse. So the rate at which, for example, if I set a motion, suppose I probably talked about this. So suppose if I have a plate and I set in motion at t equal to 0, I set it in motion some parts of velocity v, and then above it you have a fluid. So essentially what's going to happen is this velocity will actually move. So with time, different layers will start to move. Okay, and the rate at which this signal propagates will depend on the medium. So basically the diffusion of what you've done is this is a momentum that you imparted, and this momentum actually diffuses in the medium. Okay, so this momentum, the x momentum which you imparted on this plate, is actually diffusing away. Okay, and the rate and how, and if you have two different materials, for example, if you have honey versus air or water versus air, the rate at which this diffusion occurs will be different. Okay, so momentum diffusivity in that case actually is a kinematic viscosity. We have all learned that. Okay, so kinematic viscosity over there is a measure of how fast momentum can diffuse in a medium. Okay? So similarly, you will have mass diffusivity. You will have heat diffusivity, thermal diffusivity, mass diffusivity, and all right. So all these will decide your diffusive flux. And this is a general form for any property. And so now if you apply, for example, I just apply it to, let's say, reactive flow. Okay. So let's say I have a system where I have reactive mixture in a flow. Okay, so you can have a carrier fluid carrying a bunch of chemical species who maybe because of their their proximity in space while they are flowing, they can interact, they can react, okay, and form a new species, right? So while if everything is, so there's a reaction, there is a flow, and there may be as well concentration, whatever the new species form and the old species are getting consumed, that will affect their concentration. That concentration may vary with space, which may lead to diffusion, diffusive flux as well. So if you have reacting mixture in a flow, okay, which may have, so here I'm considering everything that is flow, reaction, and diffusion. Okay, reacting mixture in a flow with diffusion effectiveness. Okay. So in that case, I'll have mass balance can be written as, for example, balance as del Ca del T. So Ca would be some species, okay? There's a concentration. So number. So if you define that case, capital psi would become n number of A molecules, okay? And small psi would become basically number concentration concentration, the molar concentration of A molecules. Okay, and that would be essentially become equal to Ca. That's what we usually are referring to concentration as Ca. So for any species A, I can write down this plus del dot Ja. Now Ja, I can just write it like this equals to Ra. Okay. This is a scalar equation, by the way. Okay, and Ra is the rate of generation due to chemical reaction. In this case, if you're looking at mass balance, this is rate of, so basically it's rate of generation of psi. When, how can a number of molecule A change? It's only due to chemical reaction. Only when there's a chemical transformation, a species becomes a different species. Okay, so that would be actually possible because of a phenomena known as chemical reaction. So this is rate of generation of A due to chemical reaction. Okay, so that would be, now how do I get that? This I can find by I can do a batch experiment, find out the kinetics, how rate of change of rate of generation of it depends on various parameters, various quantities. Okay, this is obtained by chemical kinetics study in batch. You don't have to do the flow. You can separately do a rate of you can separately find out rate of generation of A in a similar in any batch process, and use that as your use that over here. So in general, chemical kinetics study again batch process. because assembling a flow process or continuous process is a bit difficult. Okay, but batch process you can do in a lab. You can take a small vessel. So medium properties may vary and velocities may vary. Now what we can do is suppose there is some pollutant which is actually so if you introduce some kind of pollutant over here, okay, or some industry has an effluent waste discharge in river at this point, then there are two phenomena will be going on. This will actually diffuse as well as will be transported with the flow. Okay, they will be both convective and diffusive, and its diffusivity will actually depend where it is in the which part of the river it is. Okay, so we have to model how does the how does the this concentration. Hello, it's a classroom. So how does the concentration profile may look like? How will the concentration profile look like at particular time, etc. With time, how will it vary? So what would be the governing equation? What would the model equation that we can form? So first thing is we can actually do some kind of simplification. There's a simplification, a very important step in extracting the mathematical model. Okay, so one simplification that we can imagine doing here is we can imagine that we will not be worried about vertical variation. Let's say that we'll assume that there is some kind of average depth average concentration we can define for this pollutant material. Okay, so we'll just be worried about the profile along x direction. We'll not be worried about profile along this depth direction. Okay? So that is first thing that's the first simplification. Remember, always start with the crudest approximation and then go to the finer details. That's how you how you actually approach a problem. You always go with the zeroth approximation first, then you go to first order, then you go to second order. So first look at the whatever the crudest approach could be, and what can you learn from the crudest approximation. Then you can refine your treatment. So the crudest, well, it's not the crudest, a little refined still. Crudest would be you can assume that all the concentration is constant everywhere. Okay? That will be the crudest, but which is wrong. Okay. The next you do is you look at how concentration may vary with spatial direction. Okay. So what would the governing equation here? So here, let's say the C is concentration of that pollutant, del C by del T plus, uh, here I'll have del by del X because del operator is basically everything is varying along X direction. So del is essentially I can just think of just del by del X. Nothing is changing along Y or Z directions. Okay. So I'll have del by del can be replaced by del by del X. Okay. And then I'll have C times Vx, that is diffusive, a convective flux, minus uh, d, which is a function of x now, into del C del x, that is diffusive flux. That will be equal to 0 because no reaction. Okay? So reaction term is 0. If you assume that those pollutant molecules do not undergo any reactions, then there is no generation or consumption, and then I'll obtain this equation. So here, what is the complication that we see is the following. You have both C and Vx varying with x. So del C by del x, Vx plus C del Vx by del x. Okay. Then, well, minus del by del x, dx, del C del x. This would be a governing equation. Here, my diffusivity, one thing that we didn't see, we didn't meet earlier is that D we were taking constantly outside because we are assuming it to be constant. But here, I have D appearing inside the derivative because the material surrounding is changing from point to point, and therefore we can assume we probably need to take D as a function of x. But if you're sure that over the concerned length of or concerned span of river, the river medium is not effectively being changed, then I can further simplify and take this D outside. Okay? All right, so that is just one special case. Another example could be So another example could be, for example, vehicular traffic flow. These are the real life examples where all this analysis will be useful and it can give you quantitative results. Okay, so traffic flow. Now there is a very the reason I'm bringing this up because there's a very important modeling approximation. There's a very important approximation which which is frequently associated with your modeling efforts, and that is something known as coarse graining. What does that mean? Okay, so well, if you look, so here, so that this example probably illustrates what the meaning of coarse graining. So coarse graining is you imagine in reality consists of discrete objects, okay, but you imagine it to be like a container. So if so, basically, so suppose you have a bunch of particles, okay, a bunch of particles, okay, like this. Suppose I have a medium where particles are spread like this, okay, something like this. Okay. Now you can see that probably is dense in this region, less denser, and further less denser. So I can smear out these individual entities. I can imagine. So one very important step is basically the thing is that to track all particles separately. If you treat it like a multi-particle system, then tracking each particle separately would be a bit difficult. Okay? that will that will involve a lot of effort tracking each particle because there is a number of particles. However, this problem can be simplified and physics or physical results can be actually, we can get some sense of what may happen by simply assuming that, okay, what we are going to do is we'll assume that this part is smeared out, okay, and so basically you can kind of do average number, you can define something called average number density. Okay? So you can, at each point in space, you can define an average number density. Okay? So rather than talking of particle entity, so you have particle, what you've done is actually you've changed this information which pertains to particles or discrete objects, basically. Okay, you have changed it to something called field. Okay, field is a quantity that is defined at each point. If you remember, I have defined that in mechanics class. Basically, it's basically you average. Here, it's basically average density. Okay, so when you say that, okay, I suppose at this moment of time, this is the places where particles are located at. I may say that, okay, this is like having density of some value in this range. Okay, in this range, what I may do is I may calculate this entire volume and calculate number of particles, divide number of particles by the volume. I'll get an effective density in this range. Okay, and then I say that, okay, this range of discrete objects can be replaced with a continuum or like a smeared out, those particles are smeared out over this entire range with that particular number density. So that would actually violate the reality, because remember, when you say there's number density of this much, you're inherently assuming that here also the particle is present. Okay, when you smear out, you are actually letting the same particle be present everywhere with certain density, right? So but in reality, that is not what's happening at this point. For example, there's no particle in the real phenomena, reality. There is no such no particles are present at this moment, but at this point, but when we approximate it with the average density, then we are assuming inherently that, okay, every point is occupied by some particle, okay, in a continuum fashion. So that is, so basically particles are replaced by field, or I should say continuum. Okay. So now to do that, then you're actually, you have to track, only thing that you have to now track is density, particle density. Okay, you don't have to track where is each particle at each moment of time. Okay, that would be a significant computing effort. But if you imagine that to talk in terms of density of particles, then you are only concerned with density, and that basically reduces your modeling effort by significant fraction. Okay, and all you need to do is just talk about density, and then density we already have a modeling. We know how density may vary because we can define flux in this case as well. Okay, so now so generally you can define density of traffic. Hello. Okay. All right. So you can define density of traffic. Like for example, here I can say density of traffic, which I'm going to call, let's say N, which is averaged density. And let's assume that things are only changing along, this is the direction of the road. So things are only changing along X direction, the things changing along Y direction. Okay, so you can average with respect to X only. You don't worry about Y direction or perpendicular direction or lateral direction. Okay, so this is average in X. N could be, for example, N can be defined as delta N by delta X. Okay. That's my definition of density. You can choose a very small strip of size delta X. Okay. Find out total number of cars or vehicles present in this strip. Choose delta X to be sufficiently large. You cannot choose. Definitely, they should be larger than the dimension of the object. Okay, so that's where it's very. So whenever you this kind of considerations become very important when you talk about porous media, where you have discreteness in the medium, and you want to approximate it with the continuum approximation. Okay, so that's where these kind of considerations become very important. Okay, we may have time to talk about that when we talk about flowing porous media. Okay, all right. So this is delta n by delta. So that would be your average density, and additionally you can define a kind of average speed. Okay, that would be, I'm going to call, so every cross section you can define a kind of net average speed of this would be basically associated with the flux, convective flux, the vehicles. Okay. All right. So if that is the case, then I have a very simple relationship that would be as del n by del t from then plus del by del x into nv over 0. Okay. So this is the equation that may govern your coarse-grained model, where you have replaced the discrete entities with a continuum system, okay, by certain definitions, involving certain definitions like this, okay, and if you do that, then you can now talk it. You have a very simple looking equation which you can actually solve using the boundary conditions, etc., and find out an average density of how that density of traffic may change with t and x. Okay, so all right, so that is another example. Um, one more example, maybe a couple of more examples, and just to get you accustomed to the kind of problems we'll be seeing. Okay, one example is, for example, that involves reaction both, but no convection. And this would be, for example, if you have a catalyst particle, okay, immersed in a medium, so you can have a spherical catalyst particle, let's say, and you can have it immersed in a medium where certain concentration of the species A is there. Okay, this is basically related to heterogeneous catalysis, and that's a very important process uh, chemical engineering, refineries, etc. So you have a catalyst particle and you have some species A, and that species A, when gets in contact with the catalyst, it undergoes chemical transformation. Okay? So this is heterogeneous catalyst. Catalyst is probably you all know about that, where you have two different phases. This is solid phase. This is liquid phase. This is solid. This is liquid. Okay, and so now this in order to so now this is just for probably for petroleum people. I'll just elaborate it a bit. Uh, so basically, this is surface phenomena. So more the surface is available, the more transformation is possible. So if you want to achieve a larger chemical transformation of species A to B, that would happen only when you have a catalyst available, with your catalyst surface available. Then you would require this transformation will be promoted provided you have more surface of catalyst available. And so therefore you would like to have this particle have a particle offering more and more surface area, and that is possible when you make it porous. Okay? So that is so you have lots of pores. You basically, in order to achieve, well, basically in order to, for example, this catalyst particle or this solid particle. Remember, this happens because of the chemistry that that is involved in reacting A with the species which makes up the chemical makeup of S and A. They actually play a role, right? So now, if you think of if you think of a particle like this, and A coming over here and then just interacting with its surface molecules of this catalyst particle, solid particle, then what you're doing is actually you are actually missing out a lot, because all the bulk part, there was a potential of these molecules which could have helped in chemical transformation, but you are actually missing it out. Okay, how would you access those bulk part? Well, you can make tunnels into it. Okay, so you can make pores into it, and more porous you make, more you are able to access the bulk part of this. So if you have more walls over here, more surfaces are offered, you are actually more efficiently utilizing this catalyst mass in achieving a chemical transformation which you desire, right? So that's why it's always there's a very significant effort goes into making these particles as much having as high porosity as possible. Right? So you will have basically the point of the matter is that you have a porous particles. So this I have a porous catalyst particles. How you make them porous? That's a different ballgame altogether. We'll not worry about that. Given porosity, etc., how we need to model it. Okay, so we will model again it as a. We'll assume that porosity is continuously distributed. Okay, so like not discrete but continuum, and so inside these pores, there will be particles coming over to surface, and then they will diffuse into it. Okay, they'll diffuse into the pore. So there will be convection can be ignored inside these pores. Okay, there is a convective. There is no convective transport inside the pore. Okay, no convective transport inside the pore. Convective transport will be outside the pore. There's a big liquid will be actually flowing this way, and that would lead to Ca being convectively transported from, let's say, from top to bottom. But inside the pore, there is no convective transport. There is no significant bulk velocity that would actually that will basically transport the particles stay inside the pores. Okay, so there will be only diffusion that is occurring inside the pores. Okay, so the relation becomes now del C by del T at any point inside the reactor, inside the catalyst particle. Okay, so inside the particle. So what you are interested in is actually finding out the reactant or the products, reactants concentration profile that may develop inside this catalyst particle. Okay, you want to find out what is the okay, there's a question on it. How are we writing convective component? How are we writing convective component? Meaning what? Okay, let me come back to the question little shortly. Let me finish this discussion. Amir, I'll come back to the question shortly. Just hold on. Now, del C by del T, and then plus, there is no velocity. So if you recall del dot, um, so here, what I'm going to assume now is basically, um, well, we can actually think of a similar problem first. We can think of a similar problem first where I have a I have a simplified problem where particle has this kind of shape and your transport is occurring, diffusion is occurring this way. Okay, diffusion occurring this way. Okay, so we'll assume that it has only one dimensional diffusion. Okay, so only one dimensional diffusion, which is along x direction. Let's say x. This will actually be not applicable here because now whatever equation we obtain here will not be applicable here because this is a we have to work in spherical coordinate system in this spherical catalyst particle. But if you have a rectangular kind of particle, then you can write a simpler looking equation that would look like del dot. Now CVX, so Vx is zero, so that is zero, so convective transport and d del C del x with the minus sign equal to rate of generation of A, let me call it A. When A is being consumed, I can write down as ACA raised to N, whatever that kinetics, assuming that we already know the rate law. This is called rate law. Okay, so that would be your governing equation. Okay, so well, and then you can assume that D is constant, I can take it outside. Okay, del CA del T minus D, and del will become del by del x in this particular case. Okay, so that would become D into del square CA by del x square equals to minus del CA square. Okay, that will be a governing equation in rectangular coordinates. But if you want to switch to this kind of the problem where you have particles are spherical, then this derivative will change. Okay, this second derivative you all probably know how to go from rectangular to spherical coordinate system. Okay, so that would change, and suppose you do not know even suppose you even do not know that, even then you can obtain by just doing a balance. If you take a spherical shell like this and do the balance, basically rate of accumulation minus rate of generation. Well, rate accumulation will be equal to rate in minus rate out plus rate generation. If you do that balance inside this shell, you'll recover the equation which would be applicable to spherical catalyst particles. All right. So we will see that equation, but at the moment, I'm just going to write it in the rectangular coordinate system. Okay? But I want you to perform this, so I'll just probably do it as homework. Obtained, well, let's say, apply balance equation to obtain the models for model for reaction and diffusion inside a spherical catalyst. Okay. Well, this is a homework which you can find easily the answer to. If you are not able to do it yourself, many of the books will be doing it. Hello, class member. Class. Hello. Okay, so okay. So please try that and just see how. Hello, my class. Hello, my classroom. Class. Okay, okay. Um, okay. So that would be another example where one term that we saw earlier was present in the previous example, that the conjunctive transport is absent. Okay. Another example, for example, let's say, yeah, well, maybe flow through packed bed reactor. Let's say. So flow through packed bed reactor. Well, that is kind of more complicated version of flow through a porous media, which petroleum engineers are concerned about, except that in petroleum engineering applications, there is no reaction. Okay? You have you have a flow that is occurring through a packed bed, which is rocks. Okay, so rocks can be considered as like a bed of small grains, right? So same thing happens, same kind of problems occur in chemical engineering as well. Only thing is that more complication, there's a little bit more complication involved, which is you have reactions going on. Okay, so okay, so that could be, for example, the model equation could be written very easily. Let's see. So what I would write. So well, here just write down del CA by del T. So let's say A goes to some products, okay, in a packed reactor, okay, and so packed reactor you will have lots of grains, okay, packed together, okay, and you'll have fluid flowing through here. Let's do simple packed. It's not exaggerated, but the fluid which is carrying some, there's a carrier fluid which is carrying the reactant, and those reactants, when come in contact with these wet particles, they react and produce something. Okay, and there's a kinetics of that which we already know. So I know I have a RA. Okay, that's from kinetics studies. Okay, so so here now. Now, I'm not interested in the what's happening inside the particles, but I will be probably writing what's the concentration outside over that in the back bed itself, not inside the particle, but in the this region where the fluid is there. Okay? Where the fluid is there, what is the concentration? How does the A concentration changes with P and etc. What is the model equation of change in A? So now you see the problem is of different nature. Okay, and here I have uh, v, let's say v something known as nominal speed, nominal velocity. Okay? Nominal velocity. What is nominal velocity? Well, if you look the nearby spaces, okay, if you look at these spaces, so you'll have, well, maybe I can show this like this. I have a full process with that. So this is what I have actually kind of magnified over here. Okay? This is a magnified view of your bed. Okay? So you can say that this probably looks like this. Okay. Now here there will be some kind of velocity v naught, okay, which is called nominal velocity by which this fluid will be actually moving this way. Now this velocity, why is it called nominal velocity? Because that's what we can measure. Okay, something can be measured. This can be measured. The real true velocity, you cannot measure, because here if you look at velocities, they will be having all possible directions because fluid will be will be carried away like this. Okay. Flow patterns is completely unknown because it's very randomly packed medium, and you do not, there's no way to predict how the flow may occur. Okay, so flow may look like this, I do not know. Okay, But overall, whatever be the flow, this has to the flux condition or the continuity will be satisfied by the flux will be decided by the V naught itself. Okay? All right, so that's why it's called V naught. That's why it's important, and it's named as nominal velocity, and that is something that we can actually measure by our external variables. Okay, true velocities we cannot measure. Okay, true velocities. of the fluid cannot be. Well, if you have very sophisticated, this way can be measured, but you have to have very sophisticated setup, etc. Okay, when you measure easily. Okay, all right. So now, if you just write down the equation of balance for this, del CA by del T plus then by, let's say that I'm just worried about variation from x direction again. So one dimensional problem in space. So del by del x CA into dx. Okay. Now Vx, I'm going to assume that it's the same as because flux will be decided by V naught, so that will be V naught. Okay. That's nominal velocity. And plus, let's say it's a possibility to have axial diffusion. So assume we can further assume there's an axial diffusion. Species. Axial meaning species can diffuse away in the x direction. Okay. Okay. So if that is the case, then I'll have minus del by del x d del c by del x equals to RA can confirm whatever is known to me from batch experiment using these set of particles, we can actually find out RA. Okay, so that would be your, this V naught can be taken out, okay, and D can be taken out. You have a equation that will govern the rate of change of CA with T and X. Okay, okay, all right. So these are certain examples we can imagine which are useful here. now, 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 one thing, one very important part in this course would be to numerically compute the answers. Okay, so I am assuming that you are making yourself familiar with MATLAB. Meanwhile, so please do that. If you've not already started doing it, please start learning MATLAB because without that you will not be able to proceed with that. Okay, so so now the kind of so let me just rewrite the general equation del psi by del t plus del dotted with psi v plus this minus d psi v plus okay, rate of generation. Okay. All right. So now here, if you see, now you have derivatives appearing. Derivative terms have derivatives with respect to time and space, spatial coordinates, right? Because del would involve del by del x, etc. Here I have del by del x, and there is a del by del t over here. So you have essentially in general. Okay. And for complicated forms of this RG and velocity fields, it would be probably impossible, mostly impossible to solve it using analytical techniques, right? Using pen and paper, RK method. RK method for what? RK method for what? Well, no, RK method is not used for UD. We'll talk about that more. But RK is for ODs. Okay. RK is for ODs. I hope you're referring to the methods. They are for ODs. Okay. EDs, we have different methods. So that we'll talk in general towards the end of towards like later part of the course. Okay. But before that, we'll see at certain simplified forms of this equation, which are also useful. Okay. So what are those simplified forms? For example, some simplified forms. One case would be steady state case. Okay. Steady state, oftentimes you are interested in steady state behavior. You will not worry about if things are, if you make some changes in your setting, then you wait a little bit and then things will stabilize. Okay. So there's a transient situation, then there's a steady state situation. So steady state situation is oftentimes most of the settings are operating in steady state conditions. Okay. So that would lead to one kind of simplification where del by del t term will be 0. Okay. And in that case, I have only one independent variable. Well, one dimension, of course. Okay. So there's a one-dimensional problem, like the cases that I just talked about, and you imagine steady state one-dimensional problem, and I'll have del of del being replaced by del x. Okay. And everywhere I'll have del by del x only. Okay. So that would be that would be leading to only one independent variable, which is x. Okay. Everything else depends on this x. Okay. And this is an example of something known as ODEs, ordinary differential equations. So steady state oftentimes lead you to ODEs, one kind of ODEs. Okay. And usually these are a special class of problems called boundary value problems. Okay. So, for example, the example that we just talked about previously, in this page, this one, okay, this example, okay. This example, we talk about what is a steady state concentration profile established inside the catalyst particle over here or over here, okay. That would lead to this term going to 0, okay, and I will be having d, this is equal to that. Okay? So I can write this as, so for example, reaction diffusion A catalyst. Okay. So that would be d is squared Ca by del F square equals to K Ca is N. Okay. This is now in order to solve this, I need conditions of Ca. Right? By the way, can anyone tell me what are the conditions used on Ca for the species concentration in this? It's class from 12:45. Okay. I'll stop now. Rohit, I'm sorry. Well, we'll stop here. We'll talk this in the next class. And okay, then I'll stop the class. Any questions? And please feel free to email me if you have any questions. Okay. I'll upload the videos, last two videos this evening. Okay, and please feel free again to ask me questions, anything with you. All right, so I'll stop the class and say bye bye.